Today we're going to be learning how an atom become an ion. This is the one side of the coin. On the other side of the coin, when the same electron jump from higher state to lower state, it emit energy, which we call photon, which we human perceive as light.
I start our conversation with hydrogen atom. Let's go. This is almost a hydrogen atom. All we need to do, include an electron and there will be a hydrogen atom. So you're going to put that over here, and that is now hydrogen atom. Good. You see that the proton job is to control the electron. An electron job is to escape from the atom. By the way, this is hydrogen atom. Now, the question is, what does the proton use to control the electron? That's what we're going to try to understand. That's the question we're going to pose. What does the proton use to control the electron? We're going to draw this blue circle. We're going to make this blue circle. We're going to draw this blue circle. We're going to make it flat. Well, flat and circle is the same thing. You cut the circle by a scissor and you get a flat line. Okay. And we're going to call it N1. What is N1? You can call it a state, or you can call it level, or you can call it shell, or you can call it ground state, because this is very close to the proton. This is the ground state, this is the ground state, same thing. Now, proton uses the energy to control the electron. How much energy? E1. Proton uses E1 energy to control the electron so that electron cannot escape from hydrogen atom. So far, so good. Now you probably thinking, is it a number? Well, it is. Now you probably want to know how we can calculate this number. Well, this is how you can calculate this number. We're going to start with equation. En is equal to, of course, E1 over R square. What is R? R is the radius between the proton and the first shell. That's the R1. We're going to call R1, N1, E1, they are connected. So far so good. Now you're going to be probably wondering, what is E1? Okay, we would be able to calculate E1 as well. E1 would be H, which is Planck constant, 6.63 times 10 raised to negative 34, times C, 3 times 10 raised to 8, times R, which is 1.0977 times 10 raised to 7. You multiply them and you get E1 negative 2.17 times 10 raised to negative 18 joule. So it's energy. E1 is energy. So at the ground state, this guy has how much energy? This much energy. proton use this much energy to control the electron. This is the highest level of energy. Now, we're not going to use the joule. We're going to use a different unit. Sometimes we use, to represent the line, sometimes we use nanometer instead of meter. Of course, we know that meter is the SI unit. We should use meter, but sometimes we use nanometer. Sometimes we use, I don't know, for mass, sometimes we use milligram instead of kilogram, although kilogram is the SI unit for mass. Although joule is the SI unit for energy, sometimes we use electron volt. Joule is like a bag of energy. Electron volt is like a small bag of energy. So you're going to have to then convert this guy to electron volt. Let's do it. Negative 2. By the way, what is electron volt? Let's find it out. Let's consider a two-plate. Electron volt is a bag of energy. I told you, a small little bag of energy. Negative plate and the positive plate. And there is an electron, and there is a potential difference between these two plates. That means the potential difference is 1 volt. If electron moves from between these two plates, whose potential difference is 1 volt, we want to know the electron volt. So that gives it 1 electron volt. That gives 1, how much electron volt? 1 electron volt. Okay, so the electron volt would be Q voltage. Q is 1.6 times 10 raised to, we're going to take the absolute value of the charge of the electron, negative 19, times voltage. We have 1 voltage, so 1 voltage is how much? 1 joule over coulomb, and this is of course coulomb. Coulomb cancel, so you have 1.6 times 10 raised to negative 19 joule. All right, so 1 electron volt is that much joule. Now we should be able to see how much electron volt right here or how much electron volt right there. Let's see. So negative 2.17 times 10 raised to negative 18 joule has how much electron volt? 1.6 times 10 raised to negative 19 joule. Joule cancel. You have negative 13.6 electron volt. This is a magic number because you see it on the physics reference table. Okay, good. So instead of using these, you're going to use negative 13.6 electron volt. So far so good. Right, we are making progress, of course. Now the next thing we're going to do, we don't need that, we're going to draw. So E1 would be 13.6, negative 13.6 over R square. R is of course 1. E2, so this is the E2, and we're going to use the black to draw the E2. So this would be our E2. So N2 has E2. So the proton, when the electron is right here, when the electron is right over here instead of right over here, okay, when the electron is right there, then proton uses how much energy to control the electron? The proton doesn't like for electron to be there, because now proton going to get to use a less amount of energy. How much less? Let's find out. Negative 13.6 divided by 2 square, where the 2 come from. This is the second shell, this is the second shell, this is the second shell, second state or second level. That's where it comes from. So this is going to give you negative 3.4 electron volt. So you're going to write negative 2.4 electron volt. Okay, good. That doesn't mean, oh, of course, so this is R2 distance, R2 distance. So that's why I wrote 2 square. Now, what if electron is right here, R3 distance away? Electron doesn't have to be here. Electron can be farther away. So electron can be right here. And then it is R3 away. How much away? R3 away. What does that mean? That means you have electron is N3, which has even a smaller energy. How much is small? Let's find out. E3 would be negative 13.6. 3 square. Why 3 square? Because electron is now right here. That's why it is 3. That means electron is much away from the proton, and proton doesn't like it because proton get to use only negative 1.51 energy. So negative 1.51 electron volt. Okay, good. So now if electron is now over here, see, electron is now over here, we're going to say R infinity distance away from the proton. And proton doesn't like it because proton has nothing now to control this electron. In fact, proton has 0 energy. Proton has 0 energy to control this electron because negative 13.6 divided by infinity square, which is 0. Okay, good. Now, we don't need this. If now electron is here, say electron is here, not there, that means electron is here, and electron wants to go from ground state to N2. How much energy it needs to go there? Let's find it out. E1 minus E2 would be 13.6 minus 3.4, 10.2. Electron can move over here. From here, if it can gain 10.2 electron volt, that means it needs that much energy to move up. How much energy this electron need? How much energy this electron need to go all the way right here so it can escape the atom for good, making the atom an ion? Well, let's find it out. E1 minus E infinity, so 13.6 minus 0, which is 13.6. It needs 13.6 electron volt energy to escape the atom for good. Then the proton will have no control over this electron. That means the hydrogen atom, whether proton likes it or not, become an ion. This is the process of ionization. All right, so this is the one side of the coin. This is the what? One side of the coin. Now let me show you the other side of the coin. What do you have on the other side of the coin? How light being created, as I promised. So now let's talk about how light being created. N4 E4, N5, E5. Okay, so how light being created, that's what we're going to be talking about now. So let's say the electron is now here, electron is now here, and electron move down to here. So from N4 to N2, electron moves from N4 to N2. If electron jump down from N4 to N2, it release energy, it lose energy, it emit energy, which we call photon, which we human perceive as light. Which we human perceive as light. However, electron is not allowed to move from, let's say, this state. Okay, good. All right, now, okay, we understand that the electron can jump down this way. When it jumps down, it loses the energy. When it loses the energy, it releases the photon. When it releases the photon, we perceive that as light. That's all, sounds good. Now, what type of light does it create when it jumps from N4 to N2? Let's find it out. So E is equal to HCr 1 over n final square minus 1 over n initial square. This is a constant, and that is negative 2.17 times 10 raised to negative 18. NF, this is NF. Why? Because this is where the electrons settle. This is Ni, is because this is where it's jumping from. Okay, good. So you have 1 over 4 minus 1 over 16, because this is 4 and this is 2. All right, so E is equal to negative 2.17 times 10 raised to negative 18. You have 3 over 16, and then you're going to have E is equal to, we're going to take the absolute value. This negative means electron losing energy. Electron losing energy. So this negative doesn't mean a negative value. It's just electron losing energy. So we're going to take the absolute value. So we're going to say this 2.17 times 3 over 16 is 0.4. 0.4 times 10 raised to negative 18. And then we're going to write 4 times 10 raised to negative 19 joule. Okay, this is step 1. We're going to do 4 steps. Step 2, we know that energy is equal to frequency. We're going to make that claim. Multiply by a small number, which we call Planck constant. So that F is equal to H over E over H. So F is equal to E is 4 times 10 raised to negative 19 joule, and H is 6.63 times 10 raised to negative 34 joule second. Joules will cancel. So you have 0.6 times 10 raised to 15. So 6 times 10 raised to 14. Frequency, which is hertz. Now you're going to do step number 3. We're going to find the lambda. So velocity is lambda times frequency. So lambda is velocity over frequency. So velocity of the light is c over frequency. So lambda is 3 times 10 raised to 8 divided by 6 times 10 raised to 14. So lambda is 0.5 times 10 raised to negative 6. So that 6 times 10 raised to negative 7. All right, now we're going to do the final step. We're going to convert it to nanometer. So 6 times 10 raised to negative 7 meter times nanometer. 1 nanometer is 1 nanometer is 10 raised to negative 9 meter. So meter cancel. So 6 times 10 raised to negative 7 positive 9. 6 times 10 squared nanometer. So 600 nanometer. So this light must be blue. So this must be blue or green. All right. Okay. All right. So I hope you understand everything we did together.